Assalamu alaikum everyone, I am Ahmed Fatin Jawad from team ElectraGeniuses, and today I am going to describe to you our 6-bit SAP-1 computer. So in this computer we have our clock pulse first of all, because clock pulse is what drives the computer. It sends the clock signal and addition and subtraction is done in this computer. So then we have program counter. It's a 3-bit program counter and it can count from 000 to up to 111. Then we have our MAR or memory address register. It is also a 3-bit register. So we can see it is 3-bit input and 3-bit output. Then we have our address selector. We have our input unit connected with address selector and RAM. Input unit supplies the data from one component to another. Then we have our accumulator, arithmetic and logic unit, B register, output register. Then we have our instruction register, control sequencer, and finally our output unit and 7-segment display. So I'm going to describe these components to you. So let's describe the most important component to you first, and in my opinion this is the control sequencer. So let's see what a control sequencer does and how we constructed it. So in a control sequencer, there are 12 bits. These are different types of bits that actually controls the entire SAP computer. And these control bits are sent or recognized using opcodes. So there are 5 different instructions such as loading the data, addition, subtraction, output, and halt. So for these 5 different opcodes or 5 different instructions, we have used 5 JK flip-flops. So, and there is a reset option. Reset option is used reset option is used to terminate the current operation or process and start over from the beginning. A NOT gate is used. We can see a NOT gate is used. It is to reset a function to invert the logic level of the reset signal. And we used AND gates, OR gates. We can see these basic gates. Using this, we get 12 different outputs for 12 different control bits. Instructions sent to each component are of 6 bits because it is our 6-bit computer, so everything will be 6-bit. First 3 bits of these 6 bits are called the opcodes. And these opcodes actually define what type of instruction the component has to do. And the last 3 bit or the lower 3 bit passes parameters such as address field in the instruction. And control bits are unchanged during T-state. We know that there are different T-states. T-state actually means the time required to complete like one micro instruction. And control sequencer modifies the control bits at the start of next T-state. So this is our control sequencer. Then I'm going to describe to you our arithmetic and logic unit. These components are actually a little bit complex compared to the other components, so I'm describing them first. Arithmetic and logic unit. Arithmetic and logic unit actually does, in this computer, actually it does 6-bit addition and subtraction, and we can see that there are 2 control bits. These are called SU and EO. So SU is the addition subtraction unit of the operation. When SU is 0, addition is done, and when SU is 1, subtraction is done. And we can see there is another control bit EO. EO puts the output from ALU onto the bus if the RAM output or RO is low. You can see the RAM output or RO is low. Output is disconnected from the bus. So that means that when the RAM output is low or 0, output is disconnected from the bus. Let's see the construction of our arithmetic and logic unit. In this construction, we can see that we have used the ICs. 74LS83 IC is used. So what is this IC and why you used it? It is actually a 4-bit binary adder, and we used 2 4-bit binary adders. As this is a 6-bit computer, 4-bit from one adder is used and 2-bit from another adder is used for addition operation. And we can see that there are 6 OR gates, and these OR gates perform subtraction operation. We know how OR gates does the subtraction. And the XOR gate outputs 1. We know that the XOR gate outputs 1 when the inputs are 1 0 or 0 1, and we know that if the inputs are both 1 and 1, the output is 0. Then there is another IC, we can see 74LS245. So this IC is an octal bus transceiver, and it has 3 state outputs. And so what it does is it does the operation of EO control bits. This IC is used. Why did we use the IC? So we used this IC to control the transmission of data between the buses and also isolate the buses depending upon logic level. So this is our arithmetic and logic unit. So next we are going to show you our output units basically. So the output unit is kind of interesting because we used a converter that converts our BCD code to 7 segment. So this is our converter. We named it transmuter. It is nothing but a fancy name, but what it does is it actually follows our double algorithm method. So what is double algorithm? The double algorithm is used to convert binary numbers into BCD notation and later BCD to 7 segment. So double algorithm is also known as shift and add tree algorithm, and it can be implemented using a small number of gates in computer hardware, but it actually has a little bit higher latency, but we used it because latency is not an issue here. It is not for production or anything bigger like this. So we used it because it is kind of simple and its basic is kind of simple. So here it is, this is our transmuter. It follows the double algorithm. Here we used different types of components. This is our double algorithm, and it is connected directly from output register. It takes the input from output register and sends output to our 7 segment display and shows the result. Then we have our instruction register. So what is an instruction register? First of all, it has 6 inputs. We can see it has 6 inputs and 6 outputs, and input 3 bit moves to control sequencer. We can see that these 3 bits are directly moved to the control sequencer. These are the 3 input bits that directly move to the control sequencer, and the rest of the 3 bits are passed to the bus memory. So these are the 3 bits. These 3 bits are passed to the bus memory. So there is also different types of control bits like II, IO, clock, and reset. So when II is enabled, this takes 6-bit data from the bus, of which 3-bit is as instructions and the rest of the 3 bits is for memory. And when IO is enabled, this sends 3-bit data to bus. This instruction register is designed. Let us see about the design. It is designed using this IC 74HC74 IC, and there's like 6 D flip-flops. Using these ICs, we have constructed this, and we also can see the set, reset, clock inputs and positive with dual flip-flops. And now we are going to show you how addition is done and how the computer works, and my group mate Rafiul Islam will show you this process. Thank you.
First we run the program, then first we select the address, then at 0 position first 3 code is opcode then we select the address, then second 3 is address. Let we address the 5 position, read write, then we select the on position, opcode is 001 according to lab sheet, then at address 7 address 6 we select read and write this address, and then we go to the next position. Output there is no address selection, so then we go to next position at alt opcode is on, there is no address selection, read write, then we go to the input at position 5, here I input 2, then second input at position 6. We input second input is 2, then 2 plus 2, our result will be 4. Then we run this program. Here I see the result is 4, so add is properly work in this simulation.
So this was our 6-bit SAP computer from team ElectraGeniuses. I hope you liked our presentation. Thank you all so much. Assalamu alaikum warahmatullah.